Seeing all these number theorists, great number theorists in the audience, I feel very much out of place, like an imposter, but that's how I felt all my life. That's okay. Now, also, of course, I'm extremely grateful to Barry for having written the monumental paper that we're celebrating here today. So I tried to understand that paper for years, came to terms with it in some way. There are parts of it I think I'll never understand. But I take it in a positive way, sort of in the spirit of the Rilke quote that Yuri entertained us with earlier in the morning. Of course, even without understanding, there are various things you can be inspired by, like this picture. When I first saw this picture, this was really surprising. I don't know, Henri, maybe you felt the same way. The idea that you could sort of visualize the Hecke algebra in this way, and the way arithmetic geometry, meaning geometry over spec Z or spectrum of finitely generated rings, can be really made to come to life, was brought home by this picture, I think almost more than anything else. There was Mumford's famous picture of spectrum of ZX. That's also interesting, but for me, I think this was more inspiring and instructive in the way which is somehow combines mathematics, art, and poetry. So it's hazardous to quote directly this paper because the slides I'm going to present right after are such poor quality compared to what we're celebrating. And in fact, the latest version, after frantically typing on the plane, the latest version was submitted around 7 a.m. this morning. But I'll try my best if you'll be generous with your assessment. And I'll start with one of these dry slides of notation, which are probably not necessary for most people here because it's fairly standard number theory. Number theoretic notation, there we start with some smooth curve over a number field and choose a prime of good reduction, and finite set of places containing those of bad reduction, and all the places of K that divide P. And I'm going to denote simply by O the ring of S integers in K without separate notation for S. I'll sometimes say explicitly what set S is, but I won't bother putting it into the notation. And we will assume that we're given some integral model and an integral point, which again, I won't denote separately. I won't put a separate curly X for the model or anything like that. Okay, so there's this set of ideas I've been thinking about on and off for 20 years, and on which I've made not much progress, but other people have. So most of the time I'll be talking about the work of other people. This idea starts out with a key object that's sometimes called the QP pro-unipotent fundamental group of X bar, X base change to the algebraic closure of K. So I won't say much about this because it takes a while to develop the theory, and it's best to take it as a bit of a black box at the beginning. It's like the fundamental group, but it really is. The definition actually is up there. So it is the target of the universal homomorphism to the homomorphisms, target of the universal homomorphism to the points of an algebraic pro-unipotent group over QP. So you can imagine many such things, and this one is the initial one. And you take the target in this way. I guess I wrote pi1 of xc because, as usual, it becomes the same thing once you take this QP pro-unipotent conclusion. It's the same whether you start with the topological fundamental group or something over Q bar. So I will say more about this, but we're going to move beyond this group in a little while anyway, so I won't say much about it. So it turns out to have a motivic nature, and that's the way I guess I first introduced it as well. But this notion of a motive, as most of you know, it's still, after decades, it's not so easy to make precise. So what we think of is in terms of a system of realizations, one for every cohomology theory that we're used to. And one way to define it is using Tanakian categories of similar nature, giving rise to different realizations. So for example, you could consider the QP local systems over X bar, or the unipotent vector bundles with Platt connections. And so these are the two main things that we're going to be considering. But of course, there's also implicitly a crystalline category of unipotent isocrystals over X mod a prime of good reduction. So these are all sort of categories, Tanakian categories, you can use to define the kind of fundamental groups we're interested in. And I just briefly remark, unipotent refers to this property of being successive extension of trivial objects, like the trivial local system QP, or trivial bundle with connection OX with D. Right? So when you take the Tanakian categories, then the unipotent fundamental group can be defined by one of these fiber functor formalism, where you take, start with a local system, for example, take the stalk over a point B, over the base point B, and take the tensor-compatible automorphisms of that fiber functor. So this is one of these abstract definitions that you have to learn how to work with. Nonetheless, gives you a kind of uniform way of defining and working with these various fundamental groups. And one advantage of taking this fiber functor formalism is that it's easy to define also the unipotent set of paths or torsor of paths starting from your base point to any other point. Because given 2 points, you have 2 fiber functors, one for each point, and you can also take the tensor-compatible isomorphisms from one to the other. So this is like thinking about all parallel transports from fibers of bundles over B to the fibers of bundles over X. So now all of these kind of things have an additional structure, like a Galois action with restricted ramification and so forth. So they have further structure that I'll allude to in a moment. But at the moment, I'm just going to give you an impressionistic survey of these constructions. And you can do the same thing with unipotent vector bundles with flat connections. You can define the so-called Ram fundamental group by taking the fiber functor that takes a bundle with connection to the fiber of the bundle over B, and similarly with torsors of paths. So because I won't be using these very much, I just wrote down the extra structures that these kind of things have. So when you're considering these drum-style objects, they have Hodge filtrations and also action of Frobenius corresponding to suitable primes. So this was a theory that I developed about 20 years ago. And as I said, haven't made much progress working with it. Nonetheless, I keep staring at this diagram, which is, of course, not as beautiful as the picture I showed you on the first slide. Nonetheless, I have to keep thinking about it. So this is this diagram that starts with a point, right? And the vertical map associates to a point the torsor of paths, right? So given any point, we can consider exactly this torsor of paths for the left vertical map. Right? And the other, it's similar to the right vertical map. For the right vertical map, you can also associate to a local point a torsor of paths together with the sheaf structure or the Galois structure over KV. So those are the vertical maps. Right? And this non-abelian cohomology H1 classifies these torsors. What
are the V's in the product?
Oh, sorry about that. I should have said that. These are simply all the places of K, all places of K. Yeah. And then we're taking a product over all of them. Right. But remember that these were S integers, so at the places in S, you'll get KV and you'll get OV at the places not in S. Now, that upper horizontal map is simply the inclusion of the global points into the product of local points. And the lower horizontal map is localization. And so I didn't emphasize it here in these slides, but the key point is that when you put a suitable structure on all of these non-abelian cohomologies, this localization map turns into an algebraic map of schemes over QP and makes it into a much more amenable object than the inclusion of global points into local points. So that's the key point. In a sense, the lower horizontal map becomes an algebraic controllable substitute for that strange inclusion, Adelic inclusion. Right. So these fundamental groups also come with lower central series. They're unipotent groups. And so you have this commutator, the the lower central series in the usual group theory sense. You have to take a few Zariski closures along the way, but it's the usual thing, and associated quotients. And I don't want to go into the structure theory much today, but I will remark that one of the things that makes this fundamental group much more amenable than other types. For example, most of you will know that there's this pro-finite fundamental group, the tau fundamental group in the Grothendieck sense, which is an extremely important object as well. But that's very hard to study because it has all these finite quotients as floating around the determinant structure of this compatible system of quotients. But if you take this unipotent fundamental group, the main advantage is that it's filtered by these subgroups who associated graded groups, and it's possible to just express that. There's a formula for this associated graded quotient in terms of the homology. Right? And the homology, of course, is the QP-Tate model of the Jacobian. So that's something that we somewhat understand. That's hard to, but at least we understand that. So this is what makes this kind of fundamental group much more amenable than other kinds. Right, so then the previous map associating to a point at torsor and therefore having target these non-abelian cohomology groups have these finite level versions. So, and the idea or conjecture I've been working on or thinking about, other people have been working on. Oh, sorry, this is something I forgot. This is just a comment that you can try to understand this non-abelian cohomology as well in terms of these pieces. But this is just, again, expressible in terms of the Tate model of the Jacobian. So this H1 is somehow understandable when you try to see how the thing is in the middle is successively built up out of the lower levels. So that's the general idea. But now, okay, so here is the thing. I will define a filtration on the local points according to the formula. So sorry, I should have organize this slide slightly better. But let's look at this again. So the point is, there's this map from the local points to this local non-abelian cohomology. So what I do is take the image of the global cohomology in the product of local ones and take the pre-image in the rational points. In the local points of that. So in other words, what you get are the local points that are in the global cohomological image for various levels n. That's the way this is defined. So then, you can see that oh, sorry, one more thing. As I said, it's a last-minute preparation showing up here and there. Then for a given place as well, you can also take the projection, having fixed the place of P. So what we get is this kind of a filtration of the local points. So if you take a fixed local place like this, then these are the things that the subscript 1 corresponds to those things whose cohomological image lies inside the global image at level 1, and then level 2 and level 3 and so forth. So you get a smaller and smaller thing, decreasing sequence of subsets of local points that hopefully approximates the image of the global points better and better. And so then I made a conjecture about this, which was then supplemented by many people like Nathan Dogra and Alex Petz, and probably other people that I'm forgetting. So if anybody wants to chime in with better attributions, you should please interrupt, because I've been very lazy with my preparation. But there's a conjecture that was made around, I forgot, 2017 or something, and of course Jennifer and other people contributed greatly to this conjecture as well, which is that for n sufficiently large, you should actually get the rational points this way. Okay? So that's part one of the conjecture, but also equally important, which is maybe not emphasized enough I didn't emphasize enough in a lot of talks, is that this set should be algorithmically computable. That on the one hand, you should be actually getting the integral points or the rational points, but also there should be an algorithm for computing this set. So in other words, this conjecture is proposing this setup as a solution to what's called the effective Mordell problem, computing the full set of rational points given a curve and in a non-Archimedean way. Sorry, Matt? That's a good point. So I'm ignoring that point right now. Oh, sorry. The question was, I fixed the base point at the beginning, right? And so Matt's question was, do we really need to have done that? And the answer is no, but it's harder to describe if I haven't fixed the base point. So most of the time, I think I'm happy enough if I can solve this problem with the base point. So that's the real, anyways, with the base point is the analog of the elliptic curve situation, which is the analogy I like to pursue anyways. Yeah. Right, so anyway, so this is something that in some form or another has occupied me for 20 years. And there are lots of results by Jennifer and Alex Betts, David Corwin, Ishai Dan Cohen, Nathan Dogra, Stefan Müller, Jan Peitman, and Jan Wonk. Many of these people are in the audience right now. And I'm not going to list, I'm not giving a survey of the results that exist. I think Jennifer will say something about it, and maybe Jan as well. But at the end, I'm going to say more about a specific case, namely P1 minus 3 points. Okay. Yeah. Any questions at the moment? Any more questions? Right. Yes, that's right. For every n, it should be computable. Right? And for a large n, it should be actually the set of points that we're interested in. Right. I don't really need this, but I'll probably remark on this briefly. It's also possible to take, so of course, this lambda billion cohomology here is for all of K, so there's no local restriction, but I could change the point of view slightly. And first, change the global cohomology first to be those classes that are locally in the image of points. That's another way to phrase the same thing. And sometimes it's useful to think about this thing. I put that subscript F there in order to indicate these local restrictions. These are global cohomology with local restrictions, locally geometric global cohomology. And if you do this, this is where the geometry I referred to earlier really comes in. This really becomes a scheme over QP, right? Finite dimensional scheme over QP whose geometry we can study as best we can in greater detail. And so just a comment about these local conditions is that this condition of being in the Zariski closure, that's what I mean by this closure. You take the image and take a closure. That closure means Zariski closure. That condition for the V dividing P turns out to be the same as a so-called crystalline condition. It's the condition that imposes that the torsor be trivializable when you base change to B Chris. That's the same as lying inside the Zariski closure of the local image for V dividing P. For V not dividing P, it's similar, except it's more of a combinatorial study of what happens. And there's a very precise description given in a long paper, I'm afraid more than 100 pages, of Betts and Dogra. Right. And once you've imposed that condition, then you can, that is, once you've changed the global cohomology, put in local conditions everywhere first, it's useful to just restrict the localizations to the primes dividing P. And once you've done that, you can also relate it to a drum fundamental group via Pierre-Descartes theory. You take a torsor that's crystalline at some prime dividing P and apply a Fontaine-style functor to it, take a together torsor for the drum fundamental group with Hodge filtration and Frobenius. And those are classified by this or something that looks vaguely like a symmetric space. This algebraic group by one drum modulo a level of the Hodge filtration. Right. So yeah, this part of the diagram is very important for actually computing this filtration and doing various things with it. So I'll just comment on it briefly. So the point is that once you've completed this description of torsors to include this drum component, that map that takes points to torsors has a very explicit description in terms of these p-adic iterated integrals, so-called Coleman iterated integrals. And their coordinates are things that are have the nature of generalized multiple polylogarithms. You actually get multiple polylogarithms when x is p1 minus 3 point. But even generally, you take various iterated integrals of differential forms and get analytic functions that can be explicitly described. So maybe I'll also say one word about why these multiple polylogs or these iterated integrals arise. Again, an impressionistic sketch. So I'll just do it for P1 minus 3 points. That's because that's the easiest the case where it's possible to make things rather explicit easily. So if we express P1 minus 3 points in terms of coordinates like this, I hope I'm doing this right. Yeah, no, that's great, correct. And you choose a basis for the RAM cohomology and its dual, the dual basis for homology. Then these iterated integral functions are defined like this, where these integrals are exactly Kuhlmann integrals, iteratively. You start out with this first polylog, so to speak, just as being the integral of 1 over 1 minus t. And then dilog is defined to be this thing times dt over t, and you integrate that. And trilog, you take dilog, multiply by dt over t, integrate that, and so on. So iteratively, you define you define polylogs in this way, p-adic polylogs. And similarly, you can keep going with more words. To take, there's iterated integral indexed by general words in E0 and E1 that define these multiple polylogs. And this local map here, there we go back briefly to, this diagonal map here has coordinates that are described by these kind of analytic functions obtained by iterated integrals. And what I wanted to explain briefly is why do they come up? It's because, you see, when you're trying to describe this RAM fundamental group, one way of doing it is using the universal unipotent connection. That's something you can explicitly describe even in general, but for P1 minus 3 points, it's actually very simple. You take the non-commutative power series algebra generated by E0 and E1 and take the trivial bundle corresponding to that, just tensor that with OX. And then there's a connection on it given by the formula above. That first D is the ordinary D, then you have the two generating differential forms, and that E0 and E1 is just a multiplication operator on that power series, right? So with that, you get a connection. And this turns out to be the universal connection, unipotent connection. Given any other unipotent connection with the choice of an element inside the fiber over B, there's a unique map of connections that takes the base point of this universal connection, so-called universal connection, to V. As you will recall from the theory of universal covering spaces, it's the same kind of thing. Once you've constructed this universal connection, essentially the tensor of fundamental group as well as the tensor of path can be described by various fibers of this universal object. So that's the idea. And so as I said, this is supposed to be just a very impressionistic survey, so I'm not going to go into detail, but the isomorphism is so-called given by path lifting, as with universal coverings. So you get given any path on the base, you can lift it to a path on the covering that gives you an element of the fiber over the endpoint. And it's the same way this works here. And so this is kind of abstract parallel transport, but when you do this over QP, this abstract parallel transport operator can be explicitly realized using Kuhlmann integration. And that's why the Kuhlmann integrals appear inside the formula for the torsors. So that's, as I said, that's an impressionistic sketch for where those functions come from. So then the strategy for computing the filtration that I defined earlier is like this. You try to understand this localization map as well as you can. Right? And if you understand that well enough to find functions on the target that vanish on the image of the localization map, you pull that back to the points of the curve using this Duram iterated integral map. Right? Then that gives you analytic functions on these local points that kill global points. Right? And these are each time you produce some function in this way that kills global points via this diagram, you're computing more and more of the filtration that I defined earlier. That's the general idea. Okay, so that's, yeah, maybe let me pause for a second. I hope this makes overall sense. Any questions at this point? Uh-huh.
What does this look like if you just go down to the abelian, the Tate module, what's the analog?
Yeah, very good question. That's right.
What are you generalizing?
That's right. So that's a very good question. What happens is that when you go to the H1, when you replace pi 1 by H1, this part of the diagram is the usual thing. There's no difference from there. The usual thing. What happens over here? This is the Lie algebra of the Jacobian, and this is just a log map of the Jacobian. That's what happens over there. So this is.
Vertical maps are just embedding the points in the Jacobian using the base point.
That's right. Well, embedding the points in the Jacobian using the base point, then passing to cohomology via commerce theory. Yeah, thank you. Thank you for putting that. So this is just lifting that map to higher levels. Yeah. Thank you. Any other questions? Yeah. Mm-hmm. Yeah? Uh-huh.
If you, beyond the case of P1 minus 3 points,
Mm-hmm.
what do these chaotic iterated intervals look like? Do you have like explicit chaotic?
Yeah, you have. So in principle, they can always be described. You choose a basis of differential forms, holomorphic differentials as well as differentials of the second kind, and then so one short answer to your question is that the iterated integrals are obtained by just expanding them as a power series in disks, right? And then just formally integrating the power series. The tricky part is how to connect the integrals on different disks, and that's what Coleman integration is about. So-called analytic continuation along the Frobenius. Uh-huh.
Do these recover like multiple elliptic polylogarithms?
Oh, yeah, of course. Yeah, that's right. Yeah, thank you. Yeah, that's awesome. That's true. Maybe Jennifer will say more about this. I don't. Right. Any other questions? Uh-huh.
Sorry, this is really basic, but you hinted at earlier what this picture might look for the not dividing.
Right.
How is this picture different?
Well, there isn't this drum picture. Well, maybe there is, but there's not an obvious drum picture. You don't have Pierre-Descartes theory for V not dividing P. So in principle, it's more elementary, but you have to do, it becomes a more combinatorial description somehow. That's kind of the vague answer. Yeah. Unfortunately, as I said, the answer is hidden inside 100-page paper. So other questions? No, nothing a priori bound. You can bound various things. If you know the model way rank, for example, you can bound the n conjecturally. But and so yeah, so there's some a priori bound. But how long the algorithm will take, even if all my conjectures are true, it's not so clear. So in that sense, there's no bound. But remember, that's true of BSD as well. You should take the descent algorithm. There's no guarantee on how long the descent algorithm will take, right? But the conjecture is that it will terminate. How long it will take, we don't know. Other questions? Let me move on to this case of P1 minus 3 points. I just put this up here to remind people that this is also a modular curve. Right. Yeah. So, somewhat sadly, I haven't been using the modular nature of the curve. That's kind of embarrassing. And I apologize to the two of you especially for not being genuinely modular. Even though there are people working on using modular nature at the moment. Right. So a number of very nice things happened in this case, and other people have been working on this mostly, and I've only recently tried to understand what's been happening, and it's mostly due to these people, and probably names that I'm forgetting as well. But this idea, I think one name that I do want to emphasize is the first one, Majid Hadian. So he was a student of Geert Faltings, and he first urged us to look at this motivic picture, which refines the Galois theoretic picture I described earlier. And I don't know, I think he's quit mathematics or something. So what's different from P1 minus 3 points is that in that case, the system of realizations of the unipotent fundamental group can be really made motivic. You can define a fundamental group as a motive right? Because there is a well-defined category of mixed state motifs. As most of you probably know, there's this terrible derived category, a triangulated category of mixed motifs in general, but it's only for Tate motifs, mixed Tate motifs, that degenerate into an abelian category. You can actually define what they call a T structure to give you an abelian category. So in this case, you can actually define motivic fundamental groups in the sense of motifs properly, not just as a system of realizations. And these are mixed state motifs. So to say that slightly more precisely, there is this category of mixed state motifs over this ring of integers, S integers that we set up at the beginning. But what does this mean? As you know, this is an abelian category. There's various abelian-style objects. You don't normally think about unipotent fundamental groups or varieties or things like that inside there. So what it actually means is that there's a Hopf algebra inside there, and that makes sense because it's an abelian category. You can talk about maps from A tensor A to A and A to A tensor A. These are all things that exist inside that category. So there is a Hopf algebra inside here, such that when you take the various realization functors and apply it to the Hopf algebra and take their spectra, you get this realization. You get these unipotent fundamental groups that we defined earlier. So that's the sense in which you can define actual motivic fundamental groups and torsors of paths. And that's the difference. That's a special thing about this P1 minus 3 points. And it would be nice if you had such a category over other curves as well. But just adding one elliptic curve to P1 minus 3 points is very hard. And this is what would happen, for example, for the torsor of paths. If you had some other point, then there's a co-module for the Hopf algebra whose realizations give you the path torsors defined earlier, discussed earlier. Right? And you probably know this, but you can write down a set of conditions on co-modules that impose the condition that it's a torsor, that its spectrum is a torsor. Right. So what is the result? Well, I guess I should say a little bit about this category. I'm not going to say much, but give a brief sketch of how people work with these categories. Is that, well, when you have mixed state motifs, there is a canonical fiber functor to vector spaces over Q given as above. Right? So all these mixed state motifs have this property that they're filtered. There's a weight filtration that turns out whose associated graded objects are these state motifs or Lefschetz motifs. And so by looking at counting the dimension of each of these components, essentially, you get a fiber functor that goes from mixed state motifs to Q vector spaces. So when people talk about the Tanaka group of mixed state motifs, they usually mean the automorphisms of this fiber functor. So, and that's what we're denoting by G superscript MT. And what happens in comparison with the Galois theoretic situation I described earlier, in this case, you have a non-abelian cohomology again, but the group whose non-abelian cohomology you're looking at is this motivic group, not the Galois group, which is a group over Q, group scheme over Q, and you take coefficients inside the realization of the motivic fundamental group of P1 minus 3 points. Because once this group, remember, acts on these realizations, right? So this makes sense to take H1 with coefficients in that specific realization. And so the map from points to torsors can be realized inside this non-abelian cohomology, which is a scheme over Q now, not a QP scheme. And it has a slightly delicate comparison with the previous Galois theoretic thing.
Probably you don't want to say too much about it.
Sure.
It is coded slightly delicate.
Mm-hmm.
But is it genuinely going to be smaller? And what is it kind of capturing?
So
The Galois theory can't capture.
Yes. Oh, sorry. So the question is this genuinely more refined than the Galois theoretic picture? That was the question, in a sense. And probably, yes, it's not so clear. I'll say what the relation is in a second. But one thing, maybe, regardless of the answer to your question, one reason for looking at this is that it's more computable than the Galois theoretic construction, because one knows a lot about this group. And that's what I'll say in a second. So, okay, so I'll ignore this point for a second. So this is also just a repetition of the previous diagram, except we can do, all I'm pointing out is that we can do this using this motivic fundamental group and this motivic Galois group, this motivic Tanaka group as well, similar to other things, and set up various conjectures. So maybe I won't belabor this slide, even though there are some delicate points associated with this slide as well. But you can imagine that the setup is exactly the same as the previous, except in this setting, which Matt is asking, is it really more refined? But in fact, it is true. It is more refined. So this is the answer to your question. In principle, it's not. So in principle, this is smaller than this. But I don't know if this is a proper inclusion. In what situation is a proper inclusion? But nonetheless, we know that this is in any case contained inside the previous filtration. If you set up the diagram if you set up the filtration using this diagram, and roughly speaking, the reason is contained here. Again, this is the delicate point that I'm not really explaining right now. So this is simply just a map from the local points, product of local points, to this, that should have been all V as well. But to the local cohomology, non-abelian cohomology with coefficients in the previous unipotent fundamental group. But it fits into a diagram like this. So if you take points up there that become global when you send it along the upper horizontal, leftward pointing horizontal arrow. If it becomes global there, of course it'll become global down here. Right? So that's why this set is in the previous thing. That's why this set is contained inside this one. Whether it's a proper inclusion or not, I'm not completely sure. So that's also this map from the motivic classifying space to this Galois theoretic classifying space is not such a naive thing. You need some effort to define it. And then the reason is that, remember, that fiber functor was this funny dimension of graded pieces type of fiber functor, right? To get a map from there to this étal pi 1, étal QP pro unipotent pi 1, you have to do something. And I'm not going to say exactly what that is right now. Roughly speaking, you prove that that thing up there classifies all torsors, right? Then you can go back to the torsors and look at the étal realization. That's the map over here. Right. Okay. Anyways, so I need to justify why one should be looking at this motivic potentially abstract picture, right? So I'll explain that right now. So, sorry, maybe too much stuff on one slide, but I'll explain this anyway. It turns out that one of the many places where the slides are sloppy is that if you look at this motivic Tanaka group, it first of all has a decomposition written up there. It has a GM component and a unipotent component. What is the GM component? It's simply because, remember, the fiber functor ended up in graded vector spaces. It was sum over all the weights of hom from Qn to the nth graded piece, or minus 2 nth graded pieces of the realization, right? Of the motive, sorry. And so there's a grading on the target, which gives you a GM action and everything. Right? So the grading is compatible with all maps between motives. So there's a GM action. And then that E up there simply consists of those automorphisms of the fiber functor that act trivially on the graded pieces. That's the E. And that gives you this kind of semi-direct product structure on the motivic Tanaka group. Again, this as well, it's actually not that hard, but I still won't go into it much right now. But I will make one comment over here. So the abelian part, abelianization of this unipotent part is actually just a direct sum of these X groups, the dual of the X groups. And the way this works is that if you had an extension of, say, Q by Qn, right, then if you apply the fiber functor to n, you just get a two-dimensional vector space, right? So if you look at the action of E on this two-dimensional vector space, you just get a 2x2 matrix that with ones down the diagonal, 0 in the lower triangular component, and just one rational number in the upper triangular component, right? So in other words, any such extension gives you a function on E by just looking at the matrix coefficient. Right? And that function factors through the abelianization, and that's where that decomposition comes from. Then you have to show, of course, it takes some work to show that these are all the functions on the abelianization. But because it's a unipotent group, it's also, well, okay, so because of some x2 vanishing, it ends up being a free unipotent group. So the whole group, as well as its Lie algebra, just becomes a free graded nilpotent Lie algebra. So that's a general fact about free unipotent groups and free Lie algebras, that they are the free algebras generated by their abelian quotients. That's kind of a general abstract fact. So, and finally, about this general structure theory, these X groups have an explicit description in terms of K theory. Of course, the only easy portion of this is X1 of Q by Q1, which is where you get this units, right? So, but the others are a little bit hard. Nonetheless, we have this dimension formula given by Borel decades ago. And when K is a cyclotomic field, oh, sorry, I think I lost something inside this slide. But it doesn't have much substance for now anyways. When K is a cyclotomic field, there are actually explicit description of these in terms of special values of so-called motivic polylogarithms. Multiple, well, anyways, yeah. So there are situations where this is actually useful, but it's still rather abstract in this form. Right. So what you do is, for now, I'm just going to set up notation without that much content to it. You can denote, So we'll just denote bases for these various levels by tau i's and sigma ij's. And those tau i's sometimes I'll also write as sigma 1j's. And so for example, that level 1 set of bases can be chosen to be the dual of a set of a basis for the units tensor Q, right? Oh yeah, this is the thing I was going to say. I hadn't forgotten it, sorry about that. But for degree larger than 2, there's a way of constructing these basis elements as dual bases for special values of motivic polylogarithms. Yeah. Okay. I think what I'll do here is skip some of the more technical slides because how am I doing on time? Actually, I'm not doing so badly. Okay, maybe I will say a little bit about this portion because I will need it later. So if you're given a mixed Tate motive, by the way, so remember this fiber functor applied to M was this Hom thing, right? From direct sum of Qn to the 2 minus 2n's graded piece of the motive, right? But in fact, when you tensor with K, this just becomes isomorphic to the drum realization. Yeah? And the reason is this. So firstly, when you tensor with K, for any one of those pieces, these graded pieces, you just get Homs from K to the drum realization of K. That's just because of, well, the drum realization of Q minus n is just K via this standard basis elements that we've already chosen for H2 of P1. Right? And so just by dimension count, the Mabder realization functor gives you an isomorphism of this sort. On the other hand, if you look at this weight graded, direct sum over weight graded pieces of the drum realization, that's canonically isomorphic to itself, the drum realization itself. That's because for Tate motives, that weight graded quotient, this has a canonical splitting. There's a Hodge theoretically, there's a canonical splitting of the filtration, right, that allows you to just define an isomorphism between graded pieces and the drum realization. So this is going to be used in a little while. Okay, now we're moving towards an explanation for why I'm doing all this. Right? And that's because there's a certain simplification. So here's where the simplification starts to come in. Right? Firstly, the Lin, in his famous paper, that was, I guess, about 180 pages paper, that was long ago, right? Introduced this canonical quotient of motivic pi 1 of x. It didn't have the mixed Tate motive category then, so he did it in terms of realizations. But of course, it's possible with later machinery to really do it motivically. And the way he did it was that he considered P1 minus 3 points just includes into GM, right? And when you do that, you lose one of the generators, right? So that B is the subgroup generated by that generator that you've lost, right? The loop that goes around 1, right? And then the Lin's quotient is this thing. You just take the pi 1 motivic and mod out by the commutator of B by it. So that was the quotient. And this turns out to be a much simpler object than pi 1 motivic itself. So this is the whole trick that you need to do to actually make this machinery workable, is you have to pass through various quotients that retain some information, but that are actually manageable. The motivic conjugate fundamental group is easier than the profinite one, but it still has a lot of structure that you need to struggle with. And then going to quotients often helps. So let me just describe for you the structure of this, the Lin's quotient. If you take its Lie algebra, it just turns out to be a semi-direct product of this sort as a motive. So these are these higher order Tate twists from 1 to infinity, and then there's a factor Q1 that acts on that. And the crucially important thing is that the unipotent part of the Tanaka group acts trivially on the realization of this thing. So in fact, all you have is the grading. This enables you to deal with non-abelian cohomology much more efficiently. So we are using this notation for the basis of this, the Lin's quotient. So what's the upshot of all that? Is that when you take the non-abelian cohomology with coefficients in this Lin's quotient via Hochschild-Serre type of argument, you can realize that as the GM invariance of the cohomology of this unipotent part, right? And because GM has no higher cohomology, so you just get this invariance like this. But then, because E acts trivially on that target, right, that just becomes Homs. Right? And of course, you still have to take modulo conjugation by the image, but that goes away. If you take GM invariant things, so in other words, in every invariant class, there's a unique invariant homomorphism. That's where that isomorphism comes from. So then at the last thing, P, remember, was the Lie algebra of pi. Right? So this also becomes GM invariant homomorphisms of the Lie algebra. Now, so how does one use this? So I've already indicated that this Lie algebra of P has a rather explicit description in terms of these bases. L has an explicit description given by these generators for K-theory. Right? And so in some sense, that gives you an explicit description of Hom, of this Hom space, which I'll specify for you in a second. Of course, there's also this truncated version. So how do you do that? What do I mean? Well, remember, the Lie algebra has these generators, right? So given any homomorphism, this GM invariant means it has to respect the gradings, right? So it has to respect the grading. Other than that, you can send the generators anywhere you want, right? So any Hom is determined by these coordinates. So given any C, it just tells you it's determined by where it sends the generators of the Lie algebra according to these formulas, right? So the upshot of this is that, in fact, this Hom is just the spec of an explicit polynomial algebra given by the coordinates of these with respect to the generators and the basis of the target. So in that sense, in this form, the previous complexity of non-abelian cohomology, most of it just goes away, and it's a very explicitly described object, this Hom space. So there's one last technical bit I have to discuss about this, which is the localization, which is also is much more explicit than before. So that's another advantage that occurs here. So I'm just setting up this diagram that we're going to use in a second. So this is very similar to the diagram that we had at the beginning, except this localization map has a slightly different flavor. And it goes directly to the algebra of the drum fundamental group in this case. So how is that localization defined? Remember, these HOMs over here, these things are mapped from one Lie algebra to another, right? And you're supposed to get elements, local points of this drum fundamental group. How does this work? So, oh, sorry, this is what I said earlier. So you still get just a version of what I said earlier. You still get an explicit map from points to points of the curve to points of the drum fundamental group, except this looks slightly different from before because it's ending up in the Lie algebra, so that requires you to modify the previous polylograms a little bit according to a formula like this. Now, but I want to describe the localization map. So how does that work? So first of all, if you take the QP points of this modified, simplified Selmer schemes, so that the QP point is by definition, it's the map from the QP points of between the QP points of the Lie algebras. Oh, sorry, I forgot this. It's not strictly necessary, but at the beginning, I did make the assumption that P splits inside this field, right? So QP is the same as KV. So it's actually just the HOMs between the KV extensions of the Lie algebra. But that fiber functor over KV just becomes the same as the drum fundamental group itself. That's what I explained earlier via this Hodge theoretic splitting. Okay. So now, but here's the key ingredient of the localization map in this setting. If you take the KV extension of the fiber functor, remember that was isomorphic to the associated graded pieces of some of our associated graded piece of the drum realization. But then there's the Hodge theoretic splitting that I described earlier, right? But the other fact is that there's a canonical Frobenius splitting, theoretic splitting of the weight filtration in the same way. It's the sloped splitting, so to speak, of the drum fundamental group, of the weight filtration of the drum fundamental group, which then is again isomorphic to the KV extension of the fiber functor. So what do you have? You have an isomorphism from the KV extension of the fiber functor itself, right? But that's simply a KV point of this of the Tanaka group, right? A canonical way isomorphism between the KV extension of the fiber functor applied to mixed state motifs, right? So there's this canonical automorphism of that thing, which therefore gives you a KV point. And if you think about that diagram carefully, it's an element of the unipotent part. It does nothing to the graded pieces, but in fact, so it belongs to the unipotent part and gives you a KV point of E, the unipotent part of the Tanaka group. And its logarithm that lies inside the Lie algebra is what I'm calling epsilon V.
So this is basically putting the crystalline Frobenius
Essentially. So if you've already identified your, if you've already incorporated the Hodge theoretic splitting, it's essentially using the crystalline. Crystalline splitting, essentially. Yeah. That's right. But I think I prefer to say it the way I said it earlier. It's a comparison of the Hodge theoretic splitting and the Frobenius splitting. Right. So what is the localization map? What it does is it takes a homomorphisms from L to FP and just evaluates it at this point, epsilon V. It's just an evaluation map. So now the shortcoming here is that these epsilon V's are a little bit mysterious. It's not so easy to compute. They're quite hard to compute, in fact. Nonetheless, in principle, you have a very explicit description of the localization map, which is, well, explicit in what sense? Well, as most of you know, localization in Galois cohomology is quite hard, no matter what you do with it, right? By comparison with that, even if there are some unknown ingredients here, localization here is very easy. Maybe to say it even more precisely, yeah? So remember, this L was a free Lie algebra generated by the sigma ij's, right? So now free Lie algebras have these bases given by Linden words inside the generators, right? So these epsilon v's, whatever they are, can be written in terms of these Linden words. So abstractly, anyways, they have some of these coefficients written in terms of that basis for the Lie algebra. And those AW is what I'm saying are a bit mysterious. But in fact, part of it is very easy. So the lowest level thing in degree 1 is just a logarithm of these units that I chose at the beginning. You've probably forgotten about them, but there were these units whose duals gave you these tau i's, right? So that's what you get for the first coefficient, but the other things are quite hard to compute. Nonetheless, we know that, well, it can be written as a linear combination of these Linden words. Now, so of course, any element inside L just can be written as a linear combination. I'm just repeating the obvious thing that I said earlier. But then, the point is that given any element, any homomorphism from L to F, L to the realization of P, what we can do is we can certainly write down a formula for the evaluation of that on an element of L. Okay? So this looks a bit mysterious, but it's not a big deal because these coordinates are simply the values of the homomorphism on those generators, right? So you just have to do some abstract Lie theory, some combinatorial Lie theory to see what it will do to a general element, right? So you get formulas for exactly what it does to a general element inside the Lie algebra in terms of what it does to the generators. What it does to the generators are these x, y, z's. Okay? And you just express what it does. So a general Lie algebra in terms of that. Then you just get a formula like this, right? And I'm not going to write, maybe I should have, but I didn't write down the formula for you, but you get very explicit formulas like this. And what was emphasized by Ishai Cohen and David Corin earlier was that you can just look at this whole thing. In other words, you take the product of the L's, right, or the extensions to the various KVs, and take the Hom space and take the universal evaluation map. That takes a Hom and an element of the source and just evaluate it there while preserving the second component. So this whole thing can be computed. And there's an explicit expression for this as a map between affine spaces. So even though we don't know the epsilon v's, this whole space has the universal evaluation homomorphism has a formula. Mm-hmm. Oh, sorry, am I already? Yeah. 3 minutes, gosh, yeah. I think I was looking at this clock the wrong way around. Yeah, sorry. Yeah. So in that case, so maybe I'll fast forward to the results, just a few results. Yeah. So using those ideas, you can start computing various equations. So let me just tell you some of the things that happen. So this is not an extensive summary of the results that exist in the literature, right? But a few. So these last few slides are especially disorganized. This is a part I typed this morning. But here they are anyways. So when K is Q, right? So here's what happens. So if we just take S to be empty, the S integral points, the Z points for P1 minus points is empty. So the conjecture in this case is just saying that this filtration is also eventually empty. And that's all it's saying. So this is something that one can check numerically for a large number of P. And so these days we can probably go substantially further, but it's something we did quite a few years ago. So the conjecture checks out in this case. And so these authors, this was an Arizona Winter School project about 6 years ago. They checked that even if we invert 2, then the 2 integral points of P1 minus 3 points are exactly these 3 points. So this also checks out to be exactly equal to the filtration already at level 2 for the same range of P. Henri, did you have a question? Yeah, it's the same. It's the same. That's right. So I quite like this one because it has a very nice formula at level 4. So it's not giving, I think they have some specific statements about the conjectures associated to this, but rather than that, I'm just giving you a flavor of the equations for the filtration that come up when you put all this machinery together. So, and I think there are nicer ways to write down these equations, but people haven't thought about it very much because it's kind of interesting to get any formula anyway. Right. So, so here's a result in a similar vein. So if you take S to be 2 and some other prime, right? And in this case, we take the p-adic points that we're taking, we fix it to be p equals 3, right? So if you do that, then you can check that, again, the S integral point is equal to the level 2 of the filtration when L is either a Fermat prime, a Mersenne prime, or one of this set of primes. So this is the kind of computation they were able to do. And in this regard, I'll also just briefly remark that if you take the 2L integral points on P1 minus 3 points, that's strictly bigger than the 2 integral points only exactly when L is a Fermat prime or a Mersenne prime. This is a relatively amusing fact, which I think is not so well publicized. So it's kind of interesting to think about Fermat or Mersenne primes in this context. And these are what the integral points are in that case.
That too fast.
Oh, sorry. Yeah. Mm-hmm. Is this okay? Yeah. So, yeah. No. What this is, maybe I'll explain it a little bit. So what these points are is they're obviously the 2 integral points, right? And there's L because if L is of that form, for example, 1 minus L is also a 2 unit, right? And the rest of the points are just this S3 orbits of L. And the same thing down here. That's right, yeah. You have the S3 action on P1 minus 3 points. Right. So let me tell you a little bit about the quadratic fields. This is the result of Shang Li, my student, and Martin Lüke. So, so that's what happens for that imaginary quadratic field. So this part is especially haphazard. I just put together whatever I could find this morning. So if you take the Q zeta 3 and S empty, then the integral points is easy to check. These are these 6 roots of unity themselves. And that turns out to be equal to the P minus 2th level of the filtration for, I forgot which P, unfortunately, I should have checked. Maybe that's for any P possibly, but I won't swear to that at the moment. And if you allow S to be 1 minus zeta 3, this ramified prime, then you get the integral points equal to the 4th level of the whole motivic filtration in this case. And I think the last, maybe I'll skip this because I did want to say something about cyclotomic field because that was the title of the lecture. So if I didn't say anything about it, it was kind of embarrassing, right? So this is work in progress, and as I said, the slides are getting more and more haphazard, and we're rushing more and more. Sorry about that. So if you take K to be Q zeta 8, we have more results than this, but I just couldn't put it together. And you take S to be the prime generated by 1 minus zeta 8, right? Then if you apply this machinery to Deline's quotient, then the conjecture fails, obviously. Any one of these roots of unity are actually inside the infinite level polylogarithmic locus. Right? But interestingly, if you take the full motivic fundamental group, you get equality at level 4, for example, for P equals 17. And finally, the results are much better if you take the totally real subfield. So I'll just put the results on the board and not talk about it because I'm already over time. But anyways, for real subfields, it seems to work out much better. A lot of these roots of unity that cause a problem go away. Right? So there are a number of different things to investigate now, on cyclotomic fields and real subfields. And of course, among the many great things that Barry did, cyclotomic fields and real subfields are prominent example, right? So I hope to be able to produce more interesting theorems regarding P1 minus 3 points and maybe other curves over these kind of bases. Yeah. Thank you very much.